Okay, so good morning everyone. I hope I am audible here, and you can see the presentation on your screens. Is everything fine there? Am I audible? And PPT also visible?
Yes, sir.
Okay, fine. So now let us begin with the next part of what we were discussing in the last class. In last class, we have discussed how we can obtain the stress strain relations for a cubic crystal, and then we saw there that we have only how many? 1 2 3 1 2 3 three independent values of stiffness constants. Was it 3 or what? Okay, if we go back to the previous slide, let me show quickly. Yeah, so you have how many? 1. This is C11. All of them are equal. C12. This is second, and C44. So we have only 3 independent values of elastic stiffness constants. So now today we will be applying this idea uh, to actually study the propagation of elastic waves in cubic crystals. And for that, we will assume that suppose we have a big size crystal whose crystal structure or the unit cell is cubic. So make sure, what do we mean by cubic? Means we are fixing these constants according to this rule. So these constants are fixed as per this rule. So means you have only 3 independent values ofCij's. So if so, then and these values are related to actually the microscopic nature. I mean, they comes from what is the structure of the crystal, and then how this structure, um, what kind of symmetry does that structure has microscopically. Well, so let us assume a very small volume of that such a crystal whose dimensions or size are delta x, delta y, delta z along x, y, and z direction. So we are assuming a small volume of the crystal. Now you should not say why I took delta x, delta y, delta z different, not all same, because the crystal is cubic. We can take volume of any arbitrary size. It is not necessary that we need to consider a cube or cubical volume. Yeah, the microscopically unit cell is simple cubic, and that information actually will go into the relations which are relating strain versus stress. So don't try to confuse the things here. And obviously we are not using the microscopic, we are using continuum model. Till now we are using continuum model. And what do we mean by continuum model? That we don't go into microscopic details as such. Now you will ask, okay, then why we are using that stress strain tensor or a stress strain relationship corresponding to a cubic crystal? We are using theseCij's as simple numbers, which are coming from microscopic details of the crystal, but we don't bother about how those are coming, the details, howCij's are coming. We only are keeping in mind that, okay, our crystal has simple cubic symmetry, and because of that, you will be having limited number ofCij's. That's all, which is coming from the microscopic information. And to study the propagation of waves in the crystal, we shall only apply the Newtonian equations of motion. So suppose this is the volume having delta x, delta y, delta z size, and well, now suppose that on such a cubic, on this small volume, a stress is acting on x, on face x. Let us say this one is representing x, acting on this face. Now try to see things carefully. This is delta x, so this is representing x direction somehow, right? So a stress acting along this direction is x, small x, acting at any point x, let us say. So we are having a bigger crystal. So at any, suppose this face along x-axis is actually at some position x, right? It is not necessarily at origin. This corner of this cube is not necessarily at origin. This is what we are saying. So suppose this face is at some point x along x-axis. I hope it is clear to you. Now this is the stress acting on this face. Similarly, the stress acting here on a face opposite to this, parallel to this face. Now we are writing that as x. Of course, this is acting along x direction and on a face perpendicular to x direction. So this is the face. And the variation of the stress is x plus delta x. So if the stress at this point was x of x, or at x you can say, then the stress here will be the xx. This is a function of x actually. We can say this stress is a function of small x. So at some point x, if the function is x of x, then at point x plus delta x, because when we reach from this face to this face, x changes by delta x. So this becomes x of x plus delta x, stress at x plus delta x. I hope this is clear. Then how we can write down this x of x plus delta x? We can write down Taylor series. But then, okay, we don't go to the higher order terms. Then how we can write this down is that, okay, x at x plus delta x will be x at x plus, oh, I'm sorry, I have missed the delta x here. Maybe that is, just a minute, let me check if it is still there. Maybe it is hidden behind. So there will be a delta x. Of course, you know what is Taylor series. So that has been missed by mistake. So, okay, I leave it to you. I mean, here should be a delta x as well. I hope this is clear how we can write down the stress. So that net force acting on this small volume along x direction, this is a stress, right? So net stress will be the difference of the two, because this is supposed to be acting along this direction, this is supposed to be acting along this direction perpendicular to this, and then net force will be, or net stress will be, the difference of the two, because they are acting opposite to each other. And we are saying volume element is very small, so that, I mean, we don't need to consider the couple effect. So these are opposite to each other. Okay. So because of this, the net force, we can write down, the net stress will be this one, because x, this will cancel with this. So we will be left with del x over del x into delta x. That's the part here. Into, this is stress. This is representing the stress. So force is stress into area, right? Because stress is force per unit area. So what is the area perpendicular to the force is delta y into delta z. So what will be the net force? Net stress into area. So this is the force, net force acting on this small volume along x direction. Is this clear up to this point? Oh, Shreya is saying you have a question. Yes, Shreya, I just saw your message. What is your question, please? Yes, Shreya, waiting for your question. What is your question?
Sir, can you please explain how to find the tensors of the elastic energy densities? Like for xx, that is del u upon E1. So how can we solve it?
That is the assignment I had given to you. Didn't you do this?
Sir, I was not able to solve this.
Sorry?
Sir, I was not able to solve this.
Okay, you share the problems which you faced while solving them, then we will discuss it. All of you, I'll create an assignment on Google Classroom, then you share whatever you have done so that I could find out what mistakes are you doing. And maybe in the next class, we will discuss Shreya. Fine?
Okay, sir. Thank you.
Okay, so now let us proceed. I mean, okay, so this is a net force acting along x direction on this small volume. Now, there is this is not the only force coming on this small volume element along x direction. The force on this small volume element along x direction can also that can also come from shear stress. This is longitudinal stress, correct? There may be a shear stress. I mean, there may be a stress acting on, say, this face which is something like, okay, delta x, delta z, acting on this face along x direction, isn't it? So if we apply the same analysis, then what we have to write down there, the force component will be there, x of y. This face is perpendicular to y axis. I hope you remember. So there will be a force called capital X small y, which is acting here. Correct? That will be capital X small y of what? At some point, say y. And then let us say, okay, this is here, say y. You can say this one as a reference or this one, whatever. Then there will be another force on opposite face, opposite to this, that will be x small y, I mean a subscript y, then y plus delta y. Correct? Then same thing we can apply Taylor series. There this will be y, then y plus delta y, this will be x, y at x, sorry, y, not x, plus del xy over del y now, because we are saying variation of this shear strain or shear stress with the y direction. So that will be into delta y. So net stress or net shear stress along x direction because of these two stresses on these two faces will be del xy over del y into delta y, which will give a net force equal to del xy over del y into delta y times what is the area, because what is force is stress into area. So area is delta x into delta z. I hope you are able to get what I am saying. Is this clear, or you are confused? Is this okay? Are you able to get how shear stress will lead to another value or another component for x direction force? So similarly, you can try the stress along different shear force, I mean, different shear stresses. So one will be xy, there will be xz as well. So net force acting on x direction is going to be del x over del x. I mean, this is the total, because delta x, delta y, delta z will be common in all components. You will be interested, it will be interesting to see that when there is y, here will be delta y and here will be delta x into delta z. When it was x, here is delta x, here is delta y, delta z. And when there will be z direction shear stress or shear stress acting on face perpendicular to z direction, then here will be delta z and the area will be delta x, delta y. So altogether delta x, delta y, delta z will remain common. And the net force along x direction will be given by this, this equation. I hope it is clear. Is it okay, or any question from anyone? Okay, fine. I assume it is clear. Now, this force is nothing but it is equal to mass of the cube times the component of acceleration in x direction, isn't it? Force is m into a. That's why I said we are using continuum model and are applying Newtonian physics here. So force is mass into acceleration. Well, then what is mass, by the way? Mass is density. If suppose the density of the crystal is rho, then density into volume is mass. Correct? Therefore, mass is this. And what is acceleration along x direction? Let us assume u is representing displacement along x direction. So what is the acceleration? Del square u over del t square. If u is the displacement along x direction, then the force will, or the acceleration will be del square u over del t square. So that the left hand side of this equation will be, left hand side of this equation will be rho into delta x into delta y into delta z into del square u over del t square is equal to this thing on right hand side. So on both sides, delta x, delta y, delta z is common. So this can cancel. And what you shall be left with is rho into delta square u over delta t square is equal to del x small x over del x and so on. You can write to this. Anna? So now, how this information then is used to study the propagation of elastic waves in the crystal. We assume the crystal to be made up of such tiny volumes. Let us assume the whole bulk substance or bulk material is made up of such tiny volumes. Each volume is connected by certain springs. Means these springs are nothing but are representing the tendency of the crystal to go back to its original shape when it is strained. So we will be actually writing down the equation of motion for such small volume element, and then by solving the equation of motion for such small volume elements, we can accordingly find out how the waves will propagate in elastic such elastic waves will propagate in such crystals. So, well, this is going to be the equation of motion, as I have already discussed. Now, I hope you remember that's the relations between stress and strain for a cubic crystal. Now we shall be applying here those stress-strain relations for cubic crystals. So, how we can write down? So what we need to write down on y side, on the right hand side is xx. So what will be xx? Xx will be C11 small exx. This is strain. Okay, this is stress. C11 exx plus C12 eyy plus C12 ezz, because both are same, plus nothing else. So xx is equal to C11 exx plus C12 eyy plus C12 ezz. What is xy? You can find out xy is written here. That is nothing but C44. You can write down these expressions in your notebook because this will be required further. So if you write it down, that will be nice for you. I mean, you can understand things well. So xy will be equal to C44 into exy. Okay. What will be xz? So here we can't find xz, but we have seen that symmetry property. Xz is same as zx, isn't it? So xz will be C44 into exz or ezx, whatever you want to retain. C44 into ezx. I hope this is clear. In case there is any question, you type it or you can ask by unmuting your mic. Well, so what will this equation then become? This equation will become rho del square u over del t square, which is equal to C11. Now that's what came from here. We are taking this part, del exx over del x plus C12 del x. Now we have to take del xy, right? Sorry. In x there are three terms, 1, 2, 3. So when you take del, okay, I mean, rather than I explain it orally, I leave it to you. I mean, solve it quickly on your notebooks and let me know if you can arrive at this equation. All of you proceed. I'll wait for your yes, that you got it, or if you have not got it, then you can ask the questions. Please proceed. Waiting for your response. Okay, Harish says he got it. What about others? Is everyone able to get this? This is quite simple, but okay. Once you do it with your pen on your notebook, then things will be more clear. Otherwise, it remains a mystery. Sandeep got it. I hope everyone will get it. Fine. So this is going to be the equation of motion when we are going to study some uh, uh, propagation along x direction. Well, similarly, okay, what is this saying is, okay. Yeah, so this is the same equation, I think, yes, with some rearrangement. What we have done here is, okay, here we have put those what you can call UVW dependent relations, which are relating EXX with U, V and W. I hope you are able to recall them, or I need to show you up them in my other slide. Is it clear? I mean, this is where we have brought those UVWs and then their relation. So if I read it out, okay, let me quickly go back to the previous slide again. It is somewhere in my previous slides. I think I can ask you to do it yourself, but okay, rather than that, let us quickly have a look at that. Yes, that's how this is your EXX. That was nothing but del U over del X. Similarly, EYY is del U, del V over del Y. EZZ is del W over del Z, and so on. All others you will put, and you can note it down. I mean, you noted them directly, and then you have to substitute them and get the next equation. So I'm giving you time to note it down quickly, and so that you can proceed with the further step, next step. So you have to do it in your notebook. I hope you noted the relations, or they are somewhere in your notebook. Then, okay, now you proceed to get from this equation this one. Now you do substitutions and try to get things if you are able to get this. I'm sure it should be very easy. It should not be very difficult, but okay. Again, I recommend you to do this, waiting for, again, your response. You should be able to get this when you solve. First one is straightforward. EXX was nothing but del U over del X. So that became del square U over del X square. Similarly, EYY is also straightforward. So EYY, I mean, this will be something like C12 del square V over del X del Y. So this is the term here, del square V over del X del Y. Similarly, you should get all the terms. Try to collect all the terms and then rearrange them to obtain this specific equation. Okay, Sandeep says he got it. Very good. I expect others to try, please. Okay, Sakshi says also she got it. Yes, yes, very good. Everyone should be able to get this. I am sure this is simple. In case you find difficulty, you can say discuss with each other. So, okay, fine. So this is the equation now in terms of those UVW. Now here we can even get answer to our earlier question we were trying to ask. What is the relevance of those UVW? How to get, where to use them? So now once you do an XRD of your crystal, then you can find out UVWs for your crystal, and from that you can get these kind of equations, and then you can try to obtain various properties, right? Just for now, let us assume UVWs are general variables. Let's not get into whether they will come from experiment or whatever. For now, they are just the variables. Now, similarly, as this is the equation for displacement along x direction, what we had done is we had written the expression for x component of the force and arrived at this equation. Similarly, I leave it as an assignment to you. Again, I will upload the assignment. Today itself, I have uploaded that assignment for Brilliant zones. I did a delay for this because now I assume, or I don't know, whether you have forgot all those things. You should not have forgotten that, right? So this is a fresh practice. Means you should draw. If you have done it already for square, I think you would have done square lattice. You should have done that drawing of Brilliant zones. But I have given an additional assignment. There you have to try a rectangular lattice as well. So you do both and try to draw as many Brilliant zones as you can. This will be a nice exercise. After some time, you will realize, oh, the parts of the Brilliant zones are really very, very small, or whatever. You draw, then you will see this. More is the Brilliant zones drawn, higher will be the marks. So, okay, that's the assignment which is uploaded, and I have kept the date to the Sunday end. I mean, by I think evening of Sunday, you should be uploading those assignments so that you have sufficient time to get it done. Right. So, I mean, there will be another assignment for getting these two equations as well for y component of the displacement. So what you shall obtain is that for cubic crystal, you will be in a position to get y component of the displacement like this. Now, this is something interesting that for cubic crystal, you will get this kind of equations. Well, then you may ask, what if we have a non-cubic crystal? The procedure will remain same. The only things will change is this strain versus stress dependence, and then you may find out additional components here. Maybe this is not equal to this, depending upon symmetry of the crystal. And then by using those equations, we can then calculate various other things for a specific crystal. So for a cubic crystal, we can obtain how waves are going to propagate in crystal along various directions. That's the next target. So these are the basic equations, and these are not general one. These are, we can say, okay, general equation for a cubic crystal. But for non-cubic case, you have to do the exercise again, fresh, and then you may find out some different type of equations. I will not right now, but okay, I'll scan myself first. Then I may give you assignment for some non-cubic case. So stay ready for this. Anyway, right now, you don't have to do that. You have to do this part only. So please do it again, and then you have to upload the steps on Google Classroom. I will create an assignment for this as well. Well, I think things are clear up to this point. If there is any question, please ask. Or, okay. Is there any question or confusion? No. Well, also sign your attendance. Okay. Well, let's proceed further now and try to use or try to see some applications of these equations. And as an application of these equations, what we will be doing is we shall be understanding that how we can apply those equations to understand propagation of waves in 1, 0, 0 direction in a cubic crystal. So how will waves propagate along 1, 0, 0 direction in cubic crystal? What information can we obtain from these equations regarding propagation of wave along 1, 0, 0 direction? So, well, we are talking of 1, 0, 0 direction means we are probably interested in, we are actually interested in x direction, 1, 0, 0. I hope you remember what is 1, 0, 0 direction in cubic crystal. So it is a direction along x direction, you can say, or a, b, c, if these are the lattice vectors, then direction along a vector, or even you can say b vector or c vector, all of them. Because for cubic, everything looks identical when you proceed either along x direction or y direction or z direction. So the equation which we are going to use is this one. And well, let us assume that the displacement of that small volume element is defined by this equation. Now this is sinusoidal displacement. This is again that standard waves and oscillation thing. So this is representing displacement along x direction, and it will be sinusoidal with time as well as along x. And what will be the direction of propagation of this wave? Suppose you have a wave defined by this wave function. Okay, what will be the direction of propagation? I'm sure you have done this somewhere in your undergraduate classes. Oh, Sandeep is getting some question. What is the difference between strain and local strain? Strain and local strain. Strain means, I mean, you may talk about strain in a sense that it is overall bulk strain. Uh, if you take a single long wire of any material, then okay, what is the overall strain in that wire? That is the bulk strain, you can say, overall change in length of the wire to the total length of the wire. And local strain means the wire may not be homogeneous exactly. So you may have, okay, in some portions it may be a little more stretched, in some portion it may be less stretched. In case it is homogeneous, both types of strains are identical, but if there is some inhomogeneity, both may be different. Local strains may be different than the overall bulk strain. I hope that's what is the relevant answer to your question. Okay, so now, okay, I'm asking what is the direction of propagation of this particular kind of wave, which is given by this wave function? Yes, waiting for response. In which direction will this propagate? Can anyone guess or see this? Yes, yes, waiting. X direction, very good. So this is representing direction of propagation along X direction. And we are studying the waves. The displacement of the particles is also along X direction. And the direction of propagation is also along X direction. So what are such kind of waves called? Longitudinal waves. So what we are trying to study is, okay, how will longitudinal waves propagate along 100 direction in a cubic crystal? Okay. Here U, because U is the component of X displacement, isn't it? And oscillation of particle is also along X direction. So therefore, this is representing a longitudinal wave. So therefore, both the wave vector and particle motions are in X direction. Hence, this is representing a longitudinal wave. Now, if we substitute this expression into this equation, what we will get? Okay, you substitute it and let me know what you are getting. Then we will proceed further. Yes. Oh, it won't be possible for you to write it down on chat box. But anyway, I mean, you solve it, then after just a minute, I will be displaying the answer, what we are getting. So what we are going to get is something like this. Okay, now, okay, I mean, I have not done steps here. So I leave it as a target to you. You should obtain this one. Are you in a position to get this equation after substituting this into this equation? Yes. Okay, Sakshi got it. Ankush got it. Rahul, you are writing something like omega rho is this, blah, blah. It should be omega square. Rahul, it should be omega square, I think. Not omega. Yeah, good. So this is what we are getting. I'm sure all of you will be in a position to get it. Now, if we want to find out the velocity of propagation, then we can write down what is velocity of propagation. Velocity is nu into lambda, and you know what is nu into lambda. This is also omega upon k. This is very simple relation. You have done it, I'm sure. So from this equation, what we can find out? What will be omega upon k? Omega upon k will be C11 over rho raised to the power half. Just a simple rearrangement of things and simplification. So what this will give you the velocity of propagation of longitudinal waves along x direction, or 100 direction rather. We should say 100 direction for a simple cube, for a cubic crystal, not necessarily simple cubic, but for a cubic crystal, that's how we can calculate the velocity of propagation along 100 direction. Means velocity of propagation is proportional to C11. So this is how these coefficients, or how these stiffness constants are related to the physical properties. So once you know the stiffness constant, you can calculate velocity of propagation along x direction. It is inversely proportional to density, of course. So that's the interesting physical information we can obtain. Now that was the case of longitudinal wave. Now let me give a question to you before I proceed further. How we can obtain um, transverse wave propagating along 100 direction? What do you think? How we can represent transverse wave propagating along 100 direction? Think over this and try to write down something in your notebook. Okay, try to match that with what is going to come up. So the transverse waves, okay, will follow up by actually looking at transverse displacement. The direction is still same, 100 direction. So the transverse waves means the waves for which the oscillation of the volume element, say small volume element delta x, delta y, delta z, is perpendicular to the 100 direction or x direction. So that is what? V, because u is the displacement along x direction. So v is the displacement along y direction, right? So transverse waves you can obtain for the oscillations along y direction, whereas the propagation of the wave is still along x direction. You can see this is the wave which is still propagating along x direction, but the oscillation of the particles or the small volume element is now along y direction. I hope you are able to appreciate this, what we have done. Is this okay, or is there any question on this part? Could you convince yourself that, okay, this indeed is representing a transverse wave? There is one more way of getting transverse wave, and that is you may use even W. So there are two transverse modes, one longitudinal mode, of course. So one of the transverse mode is this one for propagation of the wave. There will be another transverse mode, which is, if you write down W is equal to W naught e raised to the power iota kx minus omega t. The same thing. Is it okay? Well, then how we can find out now the velocity of propagation of transverse wave? How to write down velocity of propagation for transverse wave? Now, this is the equation which is representing propagation, or this is the equation which is representing equation of motion for x displacement. But now the displacement is y. So we have to use another equation actually. The equation which we have to use is this one. I hope you now are getting the logic that how or which equation to use. So for transverse waves, we have to use this equation, which we have seen on the previous slide. Now again, the task is same. You substitute this into this equation, and then finally you should arrive at this result. Do this quickly and let me know if you are able to arrive at this result. Yes, please quickly proceed. Okay, fine. It is straightforward. So let's not consume much time on this. So velocity then Vs, we can find out velocity for propagation of transverse wave will be C44 over rho under the root. Similarly, if you try W, then also you will get the same velocity. You will get same thing. You can try it yourself. Let us try another application. Now, let us try to understand propagation of wave along 110 direction. Let us try to understand now wave propagation along 110 direction. So again for that, now here again, this slide is very important. I mean, this will actually make you familiar with how to use these equations to extract physical information. Now we are trying to understand waves propagating along 110 direction. So, okay, let me write down the displacement like this, that W is equal to W naught e raised to the power iota kx into x plus ky into y minus omega t. Now, let me ask you, which wave is this representing? Is this representing transverse wave or a longitudinal wave? Think properly, then answer. Is it representing transverse wave or longitudinal wave? Yes, waiting. Longitudinal along z direction. 110 direction. This is 110. The oscillation of the particles is in z direction. Do you think it is longitudinal? These are transverse waves, not longitudinal. Why so? Because now see, the direction of propagation is 110. So this is representing a wave actually traveling along 110 direction, and it is actually 110 when kx is equal to ky. So we have written a general expression. So 110 means kx is equal to ky. That represents a wave traveling along 110 direction. But where is the what is the direction of oscillation of the particles or volume element? That is in z direction. So now try to imagine that cube. Try to draw 110 direction, and then 110 direction is actually perpendicular to z-axis. It lies in xy plane, right? So therefore, the particle are oscillating along z direction. So what is this representing is transverse waves. Is it clear? Harish, Ankush, Sandeep, yes, please. Right, you got it correct now. So this is representing transverse wave propagating along 110 direction. So which equation we have to solve? We have to solve the equation representing oscillations in z direction. So therefore, by trying this displacement, again, this is a little lengthy thing. I mean, it may require a few steps, 5, 6, 7 steps maybe. You have to actually substitute this in this equation and then finally arrive at this result. I leave it as a homework to you. I am sure you will do this honestly and will be able to get this. In case there is a problem, we can discuss it tomorrow. So this is what we are going to get. Means omega square rho is equal to C44, kx square plus ky square is equal to C44 into k square. So k square is the overall wave vector. And actually, this is, I mean, kx, ky, we are taking different values. But for 110 direction, the component of kx and ky must be same. So we can say kx equal to ky is equal to k over under root 2. Let us say k is the overall wave vector. So that way you can write it down. But anyhow, main thing or main moral of the story is that we can write down velocity from here. What will be the velocity? Velocity will be omega upon k again, and which is equal to C44 over rho under the root. So the waves propagating along 110 direction, rather transverse waves propagating along 110 shall be traveling C44 over rho under the root. Okay. Now again, let me ask the question other way. Suppose you have to write down or understand propagation of longitudinal waves. Now what will be the wave function? Which wave function you will write down for this? Now you try to write down the wave function. The question is other way around. You write down the wave function for propagation of longitudinal waves. Yes, try your mind, try your logic, and write it down in your notebook. Again, I mean, I'm not expecting you to write it in the chat box. I'm giving you some small time to try for writing the wave function like this. I hope you all are participating in the classes. It's not like, okay, you have put your mic mute and your phone is lying somewhere on table and then you are, I don't know, doing what. I assume this is not the situation. In last class, I have noted something interesting, and okay, I'll talk about that after the class. Okay, so this is going to be the wave function representing the longitudinal wave, isn't it? Because a wave, this is not the one thing. So you have to have two components actually, the U component and V component. And U is equal to V. That will represent the waves propagating along 110 direction. I'm sure you are in a position to understand why we took U equal to V. Because if the oscillations are along 110 direction, then X displacement has to be exactly same as Y displacement. There will be some small, what you say, imagination exercise for this. I again leave it to you, and I'm sure you will be able to do this. So therefore, to study the longitudinal waves, again we have to write down the two equations, this one for U, this one for V, and then we will arrive at these two set of equations. And then, of course, since we are talking about this 110 direction, so we will actually take, so in all above cases for 110 case, you will take kx equals ky equal to something like k over under root 2, where k is 2 pi by lambda. K is related to wavelength, of course. So 2 pi by lambda. So now to solve these equations, so these are the equations which are linear equations in U and V. This represents a system of two linear equations in U and V. So now for these equations to have a non-trivial solution, okay, let us first write down the equations in matrix form. So you will be having something into UV is equal to 0, and then that something for these set of equations to have a non-trivial solution, this something means coefficient matrix should be 0. I hope you have done this in your earlier classes, and you will be in a position to do. But yes, a lot of shortcuts have been applied here. The steps have not been done in detail. And if you don't do these steps, you won't understand things. So I leave it to you again as a homework. You do this, the steps from here to here, you do it in your notebook, and then you should be able to arrive at this thing. Now, if you solve this further, you will be getting I would say quadratic equation in omega square. But you will be getting, this is something like omega square sitting here, cross multiply. So there will be something like omega 4 terms. There will be some omega square term plus some constant terms. So you have to solve that quadratic equation in omega square, and you will get two values for omega square, isn't it? Quadratic equation, two roots, and these are going to be the values. Again, I didn't solve it for you because I assume you all are senior students, and I know that you all can do this yourself. Indeed, you should be able to do this. You try it and get these values. Okay, so now based upon this, we shall be able to get two values for omega, I mean omega versus k. So from here we can write down what will be the velocity of propagation omega upon k, which will be under root of this thing divided by rho. So this will give you the velocity of propagation for a longitudinal wave along 110 direction. I hope this is clear. And there will be another set of wave. There is another possibility for longitudinal wave for which the velocity is going to be this. Now you will ask physically, I mean, how is it possible? A longitudinal wave is propagating with two different velocities. Is it possible? So basically there are two ways of looking at it. Okay, what is this part? Okay. Okay, first root. So if we focus on the first root, then first root describes a longitudinal wave and second root describes a shear wave. Okay, I mean, how do we determine the direction? Okay, we will talk about what is shear wave and what is this longitudinal wave. So let us first talk about first root. So let us take first root, I mean this one, let us take this one and then substitute this into this equation. What we are doing is we are substituting omega square rho, this equation, I mean this one, into this equation. Okay, so by doing so what you will get is this thing. I hope you can get, this is omega square rho, you put it here, omega square rho. So this is your omega square rho taken from here. This is u multiplied by this, and this is nothing but whole right hand side plus some rearrangement of things. This is half C11, C12, 2C24, K square. This is fine. And yeah, just a minute. Half C11 plus.
Sir, taking kx is
Yes, yes. What you're saying?
by root 2. Taking kx is equal to ky is equal to k by root 2.
Oh yes, yes. We have
Because
to
u
put
is equal to
K.
displacement
Yeah,
in x
correct,
and
correct.
y
Fine, fine.
direction are
We
same.
have to substitute these and then you will get the things correct. Yes, thank you. So by doing this, you will get this equation. And if you look at this equation actually, then you will be in a position to get that indeed this equation is satisfied when u is equal to v. You try this. Again, this is a little exercise you can do yourself, that you will get u is equal to v. I mean, this equation is satisfied when u is equal to v. This is representing one mode of propagation, and that is actually representing the the longitudinal wave. If you begin with another root, you will get this thing, and then finally you will arrive at this, means u is equal to minus v. So the difference between these two modes of propagation of two waves is that in one case u is equal to v, that is actually representing the longitudinal wave, and in other case u is equal to minus v, and that represents a shear wave. And to visualize that, I will need a diagram which I have not shown here. So okay, we will discuss that part tomorrow, how this shear wave propagation physically can be visualized. Okay, you try it as homework as well yourself, but tomorrow I will also help you do that. Okay, so that's all for today because time is over. And uh, if there is any question, I request you to ask if there is any question.